Davission-Germer experiment of electron diffraction. If particles have a wave nature, then under appropriate conditions, they should exhibit diffraction. Davission-Germer measured the wavelength of electrons. This provided experimental confirmation of matter waves proposed by de Broglie. So this is the experimental setup. The electrons coming from a heated gun, this is the filament, are accelerated by voltage V and made to fall on the surface of nickel target. This is the nickel target. This is the electron beam coming. This is accelerated and made to fall on the nickel target. Then from this nickel crystal, the light is diffracted, that is photon, and detector is collecting this. This is the experimental setup. This is the electron gun. Then it is falling onto this nickel crystal. Movable electron accelerator, electron detector. This is entire setup is placed in vacuum vessel. Now, Davission-Germer measured the intensity of the scattered photon from where? From this movable electron detector. Scattered photon, scattered electron as a function of angle and plotted in this form. For different applied voltages, this is the direction of the incident beam. These are the intensity of the scattered photon, scattered electron, intensity of the scattered electron. The current versus accelerating voltage has a maximum, that means there is a bump or a kink noticed in the curve. There is a kink. After the 40 volt, then 44 volt, the kink develops, it increasing. At 54 volt, it becomes maximum. The bump becomes most prominent for 54 volt, and this angle becomes 50 degree. This angle becomes 50 degree. So prominent bump will be at an angle of 50 degree, and when the applied voltage is 54 volt. According to de Broglie, the wavelength associated with an electron accelerated through V volts is lambda is equal to 12.27 or 12.28 root over V angstrom. So V is 54 volt. So putting this 54 volt, so we will get the wavelength is 1.67 angstrom. From X-ray analysis, we know that the nickel crystal acts as a plane diffraction grating, and the grating From X-ray analysis, we know that nickel crystal acts as a plane diffraction grating with grating space D is equal to 0.91 angstrom. Now this is the crystal lattices. The electron beam is coming from this direction. Electron is scattered along this direction. So with this plane, it it is making an angle of theta, and electron beam is diffracted. This is a scattered electron. This is phi. This phi is equal to 50 degree, where the maximum hump is produced, and the interplanar spacing d is equal to, for nickel crystal, it is 0.91. As the diffraction angle is 50 degree, so this angle geometrically we can prove 180 degree minus 50 degree by 2. This is equal to 65 degree. 180 degree minus 50 degree by 2. That means 130 by 2 means 65 degree. So angle relative to the family of Bragg's plane, these planes are known as the Bragg's plane, is 65 degree. Bragg's law is 2d sin theta is equal to n lambda, where d is the spacing between the crystal planes, n is the order of the reflection, Bragg's reflection, sin theta is this angle, incidence angle. It is a glancing angle. Actually, this is known as a glancing angle. 2d sin theta is equal to n lambda. Lambda is the wavelength of incident light. Now, from the Bragg's equation, this is the equation. Lambda is equal to 2d sin theta. Basically, 2d sin theta is n lambda. For the first order, n is equal to 1. So, 1 into lambda means 2d sin theta. That means 1 into lambda means lambda is equal to 2d sin theta. So lambda is equal to 2 into d means 0.91 angstrom into sine. This is 65 degree. That is already we have calculated. It becomes 1.65 angstrom, which is equivalent to lambda calculated by de Broglie hypothesis. We have calculated in our earlier slide. That is lambda is equal to, this is the lambda. For 54 volt from de Broglie equation, lambda is equal to 112.28 by root over 54 angstrom is equal to 1.67 angstrom. So now this is the de Broglie theoretical value. It can be from Bragg's law, it is 1.65 angstrom. It confirms the wave-like nature of the electrons. It is the wave-like nature of the, that means both the experimental value and the theoretical value remains same. So it emphasizes or it confirms the wave-like nature of the electrons. This is a picture of an electron microscope. This is showing an EDAX machine for characterization of different materials. Here its schematic diagram is like this. This is the image. This is from this electron source. It is coming through magnetic condensed lenses. That is the object. This is magnetic objective lenses. These are the electron paths, and this is how it works. So it is beyond our scope to know how EDAX is work, but EDAX is used on the principle of matter wave. Resolving power of any optical instrument is proportional to the wavelength of whatever radiation or particle is used to illuminate the sample. An optical microscope uses visible light and gives 500 times magnification per 200 nanometer resolution. For 200 nanometer resolution, it gives us 500 times magnification, the optical microscope. For an electron microscope, the scene is different. First electron in electron microscope have much shorter wavelength than those of visible light, and hence a resolution of 0.1 nanometer per magnification, 0.1 nanometer per magnification, 10 lakh times can be achieved in an electron microscope. This is huge. Very good its resolution. So during taking the pictures of different nanomaterials or semiconducting materials, this electron microscope gives us better characterization. We can characterize it more conveniently. Now let us do few problems on de Broglie wavelength. Problem number 1 say, if m0 is the rest mass of the electron and c is the velocity of light and the kinetic energy of an electron is equal to its rest energy, then find the de Broglie wavelength in terms of Planck's constant m0 and c. To solve this equation, we know rest energy of electron is m0 c square, where m0 is the rest mass, c is the velocity of light. So from Einstein's energy momentum relation, E square is equal to p square c square plus m0 square c to the power 4. So E is equal to root over p square c square plus m0 square c to the power 4. This E represents the total energy, which is combination of both kinetic energy and rest mass energy, as total energy E is equal to kinetic energy plus rest energy. So E is equal to Ke plus m0 c square is equal to root over p square c square plus m0 square c to the power 4. So m0 c square now kinetic energy, as the kinetic energy is the rest is equal to rest energy. So K is equal to m0 c square. So this becomes 2m0 c square is equal to root over p square c square plus m0 square c to the power 4. This is already stated. It is in the question, that is the kinetic energy of an electron is equal to rest energy. So we have taken kinetic energy is equal to rest mass energy. This is equal to 2m0 c square. Now squaring this becomes 4 m0 square c to the power 4 is equal to p square c square plus m0 square c to the power 4. So p square c square becomes 3 m0 square c to the power 4. So p square is equal to 3 m0 square c square. This c square c to the power 4, it becomes c square. So p becomes root over 3 m0 c. Now from de Broglie hypothesis, the wavelength associated with the electron lambda is equal to h by p. Putting the value of p here, h by root over 3 m0 c. So the question is, we have to find out de Broglie wavelength in terms of Planck's constant. Here it is a Planck's constant h, m0 is the rest energy, and c. So lambda is equal to h by root over 3 m0 c. Another problem, state and explain de Broglie hypothesis. Already we have discussed in our previous lecture. Show that de Broglie wavelength is given by lambda is equal to hc by root over ek, into Ek plus 2 m naught c square. Ek is the kinetic energy. From relativistic energy momentum, the total energy momentum relation, the total energy E is equal to root over p square c square plus m naught square c to the power 4. Now, E is equal to kinetic energy plus rest energy, Ek plus m naught c square. So, putting E is equal to Ek plus m naught c square, this is becomes root over p square c square plus m naught square c to the power 4. Squaring this part, left hand side and right hand side both. So Ek square plus m naught square c to the power 4 plus 2 Ek m naught c square is equal to p square c square plus m naught square c to the power 4. So taking common from this one and this one, taking common Ek common, this is Ek plus 2 m naught c square. So this m naught c square c to the power 4, m naught square c to the power 4, and this m naught square c to the 4 will cancel out. It is equal to p square c square. So Pc becomes root over Ek into Ek plus 2 m naught c square. Pc means P means h by lambda from deep Broglie hypothesis. This becomes Pc equal to hc by lambda is equal to root over Ek into Ek plus 2 m naught c square. So lambda becomes hc by root over Ek into Ek plus 2 m naught c square. So this is the equation. Lambda is equal to hc by root over Ek into Ek plus 2 m naught c square. Hence proved. This problem is similar to the previous one. Just there is a change. This change is the particle is subject to a potential, subjected to a potential field. If a particle of charge E and rest mass m naught is accelerated by a potential V, then what is the de Broglie wavelength of the particle viewing the relativistic energy and momentum relation? The relativistic energy and momentum relation is E is equal to root over p square c square plus m naught square c to the power 4. Now E means kinetic energy plus rest energy, Ek plus m naught c square. Squaring, again this becomes Ek square plus m naught square c to the power 4 plus 2 Ek m naught c square is equal to p square c square plus m naught square c to the power 4. Taking common Ek from this one and this term, from this term and this term. So Ek is equal to Ek into Ek plus 2 m naught square c to the power 4. This m naught square c to the power 4 and m naught square c to the power 4 will cancel out on both sides. So this is equal to p square c square. So Pc is equal to root over Ek plus 2 m naught c square. P means h by lambda. Putting this one, lambda becomes hc by root over Ek into Ek plus 2 m naught c square. This is just like the previous one. Now, when the particle of charge E is accelerated to potential, it will experience E into capital V, this amount of energy. So Ek becomes E into V. So putting lambda is equal to hc by E into V. E is the charge of the particle, V is the applied potential, into again Ek. Ek means E into V plus 2 m naught c square. So these two problems are almost same, just only change is the particle is subjected to a potential V and the charge of the particle is E. Properties of matter waves. The few important properties of matter waves are: number 1, the de Broglie wavelength lambda is equal to h by root over 2m ev of a particle. That means lambda of a particle is proportional to the mass of the moving particle, inversely proportional to the mass of the moving particle. This is the mass, it is inversely proportional to m to the power half, inversely proportional to the mass of the moving particle. That means if mass is more, lambda will be less. If mass is less, lambda will be high. That means lighter the particle, greater the de Broglie wavelength. So the first point is lighter the particle, greater is its de Broglie wavelength. Second one, the matter waves are not visible. Number 3, lambda is equal to h by mv. Faster the particle moves, it is inversely proportional to the velocity of the particle. If v is more, lambda is less. V means small v, velocity. If velocity is less, lambda will be more. So faster the particle moves, smaller the de Broglie wavelength. This is lambda is equal to h by mv. V is the velocity here. V more, lambda less. V less, lambda more. Number 4, de Broglie wave guides. De Broglie's wave guides the particle. So these waves are also called pilot waves. These waves are called pilot waves. De Broglie wave guides the particles. Waves will move fast than the particle. Number 5, the amplitude of the de Broglie waves associated with a moving particle measures the probability of finding the particle in space at a particular instant. So the wave associated with the large amplitude means large probability of finding the particle at that particular position. This is the figure. That means large probability of finding the particle at the particular position. As the amplitude of the de Broglie waves associated with the moving particle measures the probability of finding the particle in space at a particular instant. This is a group of waves. So these are the properties of matter waves. Now, de Broglie wavelength corresponds to microparticles and macroparticles. The momentum of the fast moving subatomic microparticle, for example a moving electron, proton, etc., whose size is of the order of 10 to the power minus 10 meter, is very small due to its small mass. As a result, the wavelength lambda is equal to h by p. So m is less, so lambda is more. We will have a measurable value. But for moving macroparticles, for example a moving car or a cricket ball, the de Broglie wavelength lambda is equal to h by p is very small. That means m is more. M more means p means m, m more means lambda is less. So wavelength is very small. For the large momentum due to the large mass, as m is more, such a small de Broglie wavelength is practically impossible to measure. Thus, a wave property is seen in case of fast moving microparticles. This can be explained mathematically with the help of the example. Let us go to the example part. If a moving car of mass 1000 kg is moving with a velocity of 100 meter per second, so lambda is equal to h by mv. H means 6.6 to 10 to the minus 34, m means 1000, kg. V means 100 meter per second. So it becomes 6.62 10 to the minus 39 meter. It is very small, very small. Visible light, its wavelength range is 780 nanometer, 10 to the minus 9 meter. So it is minus 39, but it is impossible to measure. So this value is so small that it cannot be measured. But when an electron of mass m is moving with velocity v, electron velocity is 10 to the power 6 meter per second. Its de Broglie wavelength will be lambda is equal to h by mv. So this is h, this is m, 9.1 10 to the minus 31, and velocity is 10 to the 6 meter per second. Putting this value, this becomes 7.3 10 to the power minus 10 meter. That means 7.3 angstrom. This value of lambda is a measurable quantity. Thus, when a microparticle, for example electron, is moving with high velocity comparable with the velocity of light, a wave is associated with it. Hence, quantum mechanics is applied to study its motion. However, since the velocity of a moving car is much less than the velocity of light, Newtonian mechanics is applied to study the motion of the moving car.